I'll take 2 seconds to introduce her. So it's my great pleasure to introduce Dr. Monica Taljaard as our 4th distinguished speaker in the annual Janice Pogue Lectureship. She completed her PhD degree in Biostatistics and Epidemiology at Western University in 2006, focusing on methods for dealing with missing data in cluster randomized trials. She joined the Clinical Epidemiology program at Ottawa Hospital Research Institute in 2006 as an associate scientist and now a senior scientist in the Clinical Epidemiology program and associate professor at the University of Ottawa. She's well known for her methodologic research in clustered randomized studies, but also for trying to discourage investigators from using them. So she will tell you more about that. So we've heard from Dr. Xunfu Li from PHRI and McMaster talk about the cluster crossover trials a little bit. Now we get to hear from Dr. Taljaard, who will be addressing current issues of interest in design, analysis, and ethics of stepped wedge designs, the popular cluster randomized trial design. So let's give a warm welcome to Dr. Taljaard.
Well, good evening, everyone. I never had the fortune to meet Janice Pogue. When I was invited to do the Janice Pogue Lectureship, I read everything I could about her online, and just from talking to people over the past few days and from what I read about her, she truly was an amazing individual. And I'm so sorry that I never got to meet her, but I really appreciate and thank you so much for the opportunity to share in this wonderful event. So I have a secondary title to my presentation, Dr. Strangelove, or How I Learned to Stop Worrying and Love the Stepped Wedge. Hopefully it will become clear towards the end of my talk why that is the secondary title of my presentation. So what I want to do is just, and in my talk, I'm not going to make any assumptions that you already know something about stepped wedge. So apologies to those of you who may know a lot about stepped wedge trials already, and possibly even more than me, but I'm going to start from the very basics. So I want to describe what a stepped wedge trial is and what are some of the key methodological considerations with this design. But I really want to focus on what is an appropriate justification for the choice of this design. Just because I was overwhelmed with clinician collaborators wanting to use this design, and I started worrying, but when should we be using this design? What is wrong with the parallel arm design that we've been using for years? So I really want to focus in on that in my talk today. So Xunfu has really described nicely what a cluster randomized trial is. We know that this is when patients are randomized as a group rather than separately. And one really nice advantage, and I think that's why many clinicians like the cluster randomized trial design, is that everybody in the cluster, in the same cluster, receives the same thing. So we don't have to worry about allocating individuals in the same cluster to different things. It's very simple. So that's an appealing aspect of the cluster randomized trial design. But of course, a key implication is that these observations taken from the same cluster are correlated. Because they're correlated rather than independent, the effective sample size is reduced. So there's less information coming from that cluster. So this is measured by the intracluster correlation coefficient, or ICC, which I'm going to be talking about a little bit. And it's a very important parameter in this type of trial design. So in a nutshell, what makes a cluster randomized trial different is that the unit of randomization, the unit of intervention, and the unit of observation could all be different. So we could randomize a hospital, we could intervene on the entire hospital, for example, by changing its appointment system, or we could intervene on providers within the hospitals, for example, by training them to adhere to evidence-based guidelines, or we could intervene on the patients, so we could give them drugs or treatments. But the unit of observation is the individual patient. So this is a lot more complicated to understand, and also for ethics committees to understand, than the standard patient RCT, in which the individual patient is the unit of randomization, unit of intervention, and unit of observation. So that's a lot easier to design, analyze, and understand. So cluster randomized trials have some disadvantages. As Xunfu mentioned, they require larger sample sizes than patient RCTs. They're also vulnerable to increased risks of selection biases, and that's because we often randomize clusters first, and then we recruit patients into the trial. And it's difficult to hide what arm their cluster has been allocated into. And so it could happen that we differentially recruit patients into the intervention and into the control arm, or we could recruit different types of patients into those arms. So that makes us vulnerable to selection biases with this design. With a cluster randomized trial as well, we randomize fewer units than inpatient RCT, so there's an increased risk of chance imbalance. We know that the benefits of randomization are only realized in the long run when we randomize many things. So we don't reap that much benefit from the randomization in a cluster randomized trial when there are only a few clusters. And then also they have a lot of complexities in the design and the analysis. This is just a little diagram to remind us how much the sample size inflation could be. And this could be substantial. So for example, with a cluster size of 100 patients, an intra-cluster correlation coefficient of 0.05, which is not unusual, we require 6 times as many patients for a cluster randomized trial design than for a patient RCT. So that's just something to bear in mind. And this only gets worse as the cluster sizes increase and the ICCs increase. So it's a good question to ask ourselves, should we use this design? And as Alan Donner, my mentor, used to say while he spent the first 20 minutes of every consultation trying to talk people out of doing this design, I would say yes, but only if we have a good enough reason. So according to the consort extension for cluster randomized trials, it's unethical to expose people unnecessarily to the risks of research, and because a cluster randomized trial does that and introduces additional complexities, we really need a clear reason why we want to do a cluster randomized trial. And we need to spell that out in our publications. Now, for some types of cluster trials, it's really easy to come up with a reason for using them. You will remember earlier on I said that the unit of intervention could be delivered at the level of the hospital, providers, or patients. So in our research, we have found it quite useful to distinguish between those types of trials by calling them cluster-cluster, professional cluster, or individual cluster trials. So in a cluster-cluster trial, the intervention is not divisible at the individual level. It's given once off, and it can't be separated into different pieces to give to different patients. A professional cluster trial gives the intervention to a provider. Once you've trained them to adhere to some guidelines, you can't untrain them to not adhere to those guidelines on the next set of patients. So that's a professional cluster trial. In those two types of trials, we have no other choice but to use cluster randomization. So the choice of the design is clear. But in an individual cluster trial, where we are giving drugs and treatments to patients, we need a clear reason for choosing cluster randomization, because often an individual randomized design is feasible and often preferable. So that's just a side kind of comment. One reason that people typically or often cite for choosing cluster randomization is to avoid the risk of contamination. And that's when individuals in the control arm get exposed to the intervention, and that would lead to an attenuation of the intervention effect. So the effect size would be reduced towards the null. However, rather than switch to a cluster randomized design, it could be preferable to just increase your sample size, stick to the individually randomized trial, but power it for an attenuated treatment effect. Because the sample size inflation under that attenuated sample size calculation could be less than the sample size inflation under cluster randomization. So if you do the calculations, for example, with a cluster size of 100 and an ICC of 0.05, you can tolerate up to 60% contamination before the sample size inflation under cluster randomization begins to, under individually randomized designs with an attenuated treatment effect begins to exceed that required under cluster randomization. So I'm definitely not saying we should design trials with 60% contamination. I'm just saying that we really should be anticipating substantial contamination before that becomes a good enough reason to choose cluster randomization. So what are some common reasons for choosing a cluster randomized trial design for individual level interventions when individual randomization is theoretically feasible? Well, there are situations, obviously, where that's a good design. And one is when the scientific question of interest pertains to group level effects. So for example, we may be interested in studying the effect of a vaccine not just on those individuals who received the vaccine, but also the individuals in the same community who benefit from herd immunity. So that's a good scientific reason that requires us to use cluster randomization for an individual level intervention. But there are also other reasons that I think are more difficult to justify, more difficult to kind of give hard evidence to your funders and to your peers and to your colleagues and to ethics committees as to why you should choose cluster randomization. Increasingly, we are seeing people say that they wanted to use a cluster randomized trial in order to be more pragmatic and externally valid, in that they can include whole clusters in the trial under a waiver of consent. Well, that makes one feel a little bit uncomfortable because it seems to be as if a waiver of consent is being conflated with cluster randomization. If the cluster randomized trial is okay with the waiver of consent, then perhaps individual randomization is also okay with the waiver of consent, because there's nothing about cluster randomization inherently that says it's okay to give individual level interventions with the waiver of consent. And vice versa. If you do an individually randomized trial with consent, it should also be a requirement in a cluster randomized trial to require consent for that individual level intervention. So it just is a caution that we have to be thinking carefully about why we want to do a cluster randomized trial, but it's not to avoid seeking informed consent, and it's not because we are trying to make it seem as if a waiver of consent is necessary for the ethics committee. So here are some of the main types of cluster randomized trial designs. Like I said, the parallel arm design probably is the most commonly used design. Half of the clusters are allocated to the intervention, the other half are allocated to the control. This doesn't have to be once off. It can be done in batches or staggered through time. We can also do a parallel arm before and after design, in which we observe outcomes both before and after the intervention. The cluster crossover design was explained by Xun Fu. And then the topic for today is the stepped wedge. So this is the fourth possible design. Now, what is a stepped wedge design? So I should say it's a new type of cluster randomized trial design with a rapid rise in popularity. I think its popularity has outpaced its methodological development. People are so eager to use it, but they don't have methods for it yet, so they just make it up as they go along. We definitely need a lot more methodological development, and hopefully that will happen by the end of my talk. I would not have talked you all out of doing methodological research for stepped wedge trials. So here is the basic version of the design. It's just repetition from what Xun Fu has said in the basic version, and there are many, many possible variations of this design, but all of the clusters start in the control, and then they gradually cross over to the intervention until by the end of the trial, they are all in the intervention condition. So the randomization here is with respect to the timing of implementing the intervention. The outcomes are assessed repeatedly through time. In every cluster period, we take measurements, and this is all synchronized in calendar time. So you can imagine that logistically, this could be quite difficult to set up and to manage. So there are many, many variations. As I've said, here is just a collection of some of the diagrams that I've seen. Sometimes they help, sometimes they serve to confuse you even more, but things get really, really complicated. The designs look like they are increasingly complex. I want to, in recent years, several high-profile Canadian examples of stepped wedge trials have been published in high-impact journals. The example that I want to talk about a lot today is this particular trial, a point-of-care hemostatic test. The intervention was a point-of-care hemostatic test in cardiac surgery. This was done by some colleagues in Toronto. And basically, they found that this point-of-care-based transfusion algorithm reduced red blood cell transfusions following cardiac surgery. I picked this example because it was a really simple example, easy to explain. Here's also another example of a prominent stepped wedge cluster randomized trial, which you should recognize, which was published in JAMA. They found that among patients with heart failure in Ontario, implementation of this patient-centered transitional care model did not improve clinical outcomes. And the final example, also published in a good journal, found that an educational intervention was effective in reducing inappropriate antipsychotic prescribing in long-term care. So these are just 3 examples from the Canadian setting with more and less success. So this point of care testing example I want to come back to. It's a really nice example. So I'm going to describe it, and hopefully I don't make a mess of describing it. Basically, so major bleeding is a frequent complication of cardiac surgery, and these bedside tests have a faster turnaround time. It allows for more rapid management of the bleeding, and these researchers were interested in testing whether integrating this point of care test within the context of this transfusion algorithm reduces the risk of red blood cell transfusions. So they decided to use a step-wedge cluster trial at 12 hospitals in Canada. They don't explain their reasoning for choosing a step-wedge trial. So we are going to guess at what their reasons are and then think about whether those were appropriate. So the primary outcome was just the incidence or the proportion of patients that had red blood cell transfusion within 7 days of the surgery. They did find that the intervention reduced rates of red blood cell transfusion. They don't actually report the proportions in the intervention and control conditions, unfortunately, but they do report an adjusted relative risk of 0.91. The confidence interval excluded 1, and their p-value was 0.02. So I'm sure they were very happy about that result. Here is the transfusion algorithm. I'm not going to explain it, but except to say that when I look at that, it seems like this is something that's quite complicated. And once the doctor has been trained to use it, it's probably not possible to untrain them. So I think they had no choice but to use a cluster randomized trial design. So to me, cluster randomization is justified. Here is their design for the step wedge. It's really simple. They had 6 sequences or 6 steps, if I may. They randomized 2 hospitals to each of these steps, so they had a total of 12 hospitals. And they had around 85 patients per hospital per period. And it was a very short design as well. Each of these intervals was just 1 month long. So very simple to understand. The sample size calculation, they wanted to achieve 90% power in their design. They wanted to take an absolute reduction of 8% in red blood cell transfusions. So they wanted to be adequately powered for that. They report an assumed ICC, or intercluster correlation coefficient, of 0.095 and an average of 85 patients per site per month. So that's their sample size justification. If they had done this as an individually randomized trial, they would have required just 1,622 patients. But because they chose a step-wedge cluster randomized trial, they needed about 5 times that many patients, okay? But at this point, we're assuming that's unavoidable. The question is, could they have done another type of cluster randomized trial design that perhaps needed fewer patients? And why exactly did they choose a step-wedge design? So let's think about that as we go through. Before I get to that, let me just review some of the key methodological considerations in step-wedge trials. So they have several characteristics that complicate their design and analysis. The first characteristic, and I want to go through them. The first characteristic is that in a step-wedge, the intervention effect by design is confounded with time. Now, in a before and after design, just a regular before and after test, uncontrolled, we know that if we observe a difference, there's no way that we can say that difference is because of the intervention, right? That difference could be just because of natural changes that happened over time. So we say the intervention effect is completely confounded with time. We can't tell apart why the change happened. It's a similar situation in a step wedge. The intervention effect is partially confounded with time. On average, the observations taken in the control condition occur earlier than the observations taken in the intervention condition. So we've got a before and after there. And if there is a pre-existing trend or a secular trend in the outcomes, it could mean that we don't know if the change we observed is because of the secular trend or because of the intervention. It becomes difficult to tease them apart. And so necessarily, we need to do a model-based analysis to adjust for that time effect. And whenever we use models, we have assumptions. And we don't like assumptions. We want to rely on randomization to make everything okay, right? So with the model, we have all of these assumptions we have to deal with, and that can cause a problem. Here's an example. They evaluated a novel vital sign device for its effect on maternal mortality and morbidity. They decided to use a stepped wedge cluster randomized trial. They observed an 8% reduction in maternal deaths, eclampsia, and hysterectomies. That's a really good result. So from before to after this intervention was implemented, an 8% reduction. But then they adjusted for time. So the odds ratio without adjusting for time was 0.93, statistically significant 0.0056. After adjusting for time, the odds ratio inverted. Now there was a 22% increased risk of these outcomes, and the p-value was 0.45. And they concluded that this meant we were unable to judge the benefit or harms of the intervention, which is really a pity for such a large investment in research. We didn't have to worry about time confounding if we had done a parallel arm design. The second key methodological issue in a stepped wedge trial design is that there is an increased risk of within-cluster contamination. A stepped wedge design is characterized by the fact that every cluster receives both the control and the intervention. And there could be a risk of contamination at that time of crossover. For example, if we do a stepped wedge in a trial where the exposure times are long, so for example, patients in ICUs, they may remain in the hospital for a long time, and when the hospital is already crossed over to the intervention, patients recruited under the control could become contaminated with the intervention. So there's always that risk of contamination at the patient level. But we also have a risk of contamination at the cluster level. And that's because stepped wedge trials are notoriously difficult to manage in terms of its implementation. Sometimes clusters are so eager to participate in the research that they start before they should. So they're so eager to start, they implement the intervention before their allocated time, especially the clusters that were randomized to go last or towards the end of the design, right? They have to wait a very long time. On the other hand, some clusters may also not be ready to implement on time when they should be ready to implement. So this could lead to real interpretational difficulties. So here's an example. This is a little stepped wedge trial where they evaluate, I think they randomized hospital wards. They were looking to improve, I think it was identification or treatment of delirium in hospitals. And so the orange blocks is when they were supposed to be in the control condition. The green blocks is when they were supposed to be in the intervention condition. So that was their planned design. Here's their realized design. So the little numbers there are just the, I believe those are the numbers of individuals that were recruited and identified and recruited and followed up without any missing data. So clearly there were some clusters that just absolutely couldn't wait. They just started with the intervention right off the bat. They couldn't adhere to the schedule. But then they lost steam towards the end of 17 or 18 months. They no longer were interested in collecting data for the trial, so they just stopped. There was another group of clusters that just never started. They were randomized, and clearly they must have got their ethics approvals in place and all of that, but they just didn't collect the data. And then the investigators realized that their trial was in serious trouble, so they decided to add an extra 2 clusters on. Well, it doesn't work so well for a stepped wedge because that would be a non-randomized component of the stepped wedge. So stepped wedge trials don't scale easily. Whereas with a parallel arm design, we could have easily randomized more clusters. So this trial had a lot of difficulties, and they appropriately titled their paper, Help, Problems in a Pragmatic Randomized Stepped Wedge Trial. Here is another example. Here they chose a different way to display their challenges. And I think it's really nice to write about these things so that other people can learn from our mistakes. So I'm definitely glad to find these papers. So they randomized hospital wards to an audit and feedback intervention to improve hand hygiene compliance. The red lines is when they were supposed to implement the intervention, and the dots is where they actually implemented the intervention. And so again, we can see that there were great difficulties adhering to the randomization schedule. Some sites never implemented the intervention. Some of them just implemented it very late. They stopped data collection. And so what the investigators decided to do in the analysis is do an intent to treat and a per protocol analysis. Not surprisingly, in the intent to treat analysis, their odds ratio was 1.06, non-statistically significant. So that is adhering to the randomization schedule, analyzing sites as if they were exposed, even though they were not exposed. On the other hand, when they did the per protocol or as implemented analysis, adhering to the times when they were actually exposed, we get a highly statistically significant odds ratio and improvement of 1.67. So this makes the interpretation of the trial really difficult. The third complicating feature of the stepped wedge is that the intervention effect may vary across time. So it could be that the sites implementing the intervention early have a better or worse effect than the sites implementing the intervention late. So the intervention effect might vary across time, but that's not accounted for in our model. But the effect of the intervention may also change with experience. So time since the intervention was introduced, so horizontally like that. The longer you are exposed to the intervention, perhaps the better your outcomes become. We often see that interventions tend to either improve with time, so there's a learning effect that happens, or the converse is also true. We often see that there's a decay in the strength of the intervention, because you kind of tend to forget the training that you've received many months ago, and intervention declines towards what it was at the beginning. So if we do an analysis, we have to think carefully about whether our model accommodates the type of intervention effect that we are likely to see. The model that we are all using to analyze stepped wedge trials assumes a single intervention effect. So we have to develop methodology for when that's not the case. So here is the assumption of the standard analytical model that I've just said. So the blue line there just represents that secular trend that I've been talking about. That represents the improvement that's happening across the health system in all of the control cells. And then the red line represents the response that we are modeling in the intervention cells. And as per my assumption, there's a step change, an immediate effect, and that stays throughout time. It doesn't change through time. So if that's not the case, if this is the case, we will have to develop new methodology for that. In a parallel arm design, we have more flexibility in that we can anticipate a gradual improvement. So in many parallel arm designs where I expect a gradual effect, a learning effect, I might ask people, so when do you want your primary endpoint to be? And I might power my trial for that effect at the end of the trial. So doing something like an ANCOVA analysis for the difference at the end. So it's much more easy to deal with these types of gradual intervention effects in the case of a parallel arm design. The fourth complicating feature, I mean, we've struggled for how long to get people to account for intracluster correlation coefficients in their cluster randomized trials. Now we have to convince people to account for more complex correlations, because in a stepped wedge trial, not only do we have to account for the correlation between multiple individuals in the same cluster in the same period, but we also have to account for correlations between multiple individuals in the same cluster, but in different periods. So that's called the between period ICC. So we have both a within period ICC, that's just the regular ICC we are all familiar with, but we also have to account for this correlation over time between individuals in the same cluster, but many periods apart. And generally, we would expect that correlation to be weaker than the correlation between individuals measured closer together in time. That's kind of intuitive. If we misspecify that correlation, we can end up with a type 1 or a type 2 error. So there are also additional complexities if we have a cohort design in which we measure the same people repeatedly through time. So let me just say a little bit more about that correlation structure. So this is just kind of a matrix representation, assuming I've got 8 individuals in my cluster. in a standard cluster randomized trial design, I would assume that all possible pairs of individuals in this cluster are equally correlated. So the intracluster correlation coefficient rho, that represents the pairwise correlation among all possible pairs in my cluster. And that works well in a standard parallel arm cluster randomized trial. But in a step wedge, these measurements are taken in different periods. And so we have to distinguish between this within period ICC, those are the two individuals measured in the same period, and the between period ICC. That's between two individuals measured in the same period, sorry, same cluster, but different periods. And like I said, we would expect this between period ICC to be less than the within period ICC. Now, unfortunately, the earliest methodology for step wedge trials completely ignored that correlation decay. It assumed the same correlation structure as we would for a standard parallel arm cluster trial. So all of the correlations were equal. Now, the problem with that is that that gives us the anti-conservative results. So if we fail to account for that correlation decay in our sample size calculation, number one, we will underestimate our required sample size for a step wedge. And if we don't account for it in the analysis, we have an increased risk of a type 1 error, spurious statistical significance. So the problem with ignoring that correlation is serious for a step wedge trial. If it exists, we should account for it. So if I get back to the example, now I'm not criticizing this example. Perhaps the methodology was not yet available when they designed their trial, but they assumed a constant ICC of 0.095, so no correlation decay. And their sample size calculation worked out to 12 hospitals, 7,402 patients. If I assume a 20% correlation decay per period, they would need to double their sample size to have the same power. Now, you can make an argument that perhaps a 20% correlation decay is unrealistic for a trial that's really short duration. And I agree, it's probably a bit of a push. So perhaps a more modest correlation of 5% per period should have been assumed. But nevertheless, we do have to anticipate correlation decay in our sample size methodology. Initially, when I started helping people with designing step wedge trials, I could not believe my eyes when I saw the results of my sample size calculation. I routinely got answers such as 2. I said, oh, you need 2 clusters for the step wedge trial. Clearly, I don't believe that. I don't think I want to do a step wedge trial with only 2 clusters. So then I started looking into that, and we realized that this is because this correlation decay has not been accounted for. It gives an unrealistic estimate of the strength of these repeated measures over time. So let me now get to what is an appropriate justification for the use of the step wedge. Now, step wedge trials, as I've just said, are vulnerable to increased risks of bias. They have increased complexities in the design and the analysis, which can increase the risks of type 1 and type 2 errors. So I think it's important that we have a clear rationale for why we want to choose the step wedge. Now, coming up with the rationale for your design as a step wedge involves justifying the choice of cluster randomization, which I don't think is a real big problem in step wedge trials. Most step wedge trials that I deal with evaluate cluster level interventions or professional level interventions. I haven't seen many step wedge trials for individual level interventions. So I believe cluster randomization is justified in most cases, but we also need to justify why we didn't choose a parallel arm design, which is at less risk of bias than a step wedge. So we need to come up with a clear rationale for that. So I started thinking of what are these possible reasons why people might want to use the step wedge. And I don't know if I got this right, but I tried to sort them from more appropriate to less appropriate. I'm going to review each of them in turn and then apply them to the example and see if I can come up with why they chose a step wedge trial in this case, because they don't explain themselves. So one reason is that the Ministry of Health or some government department has decided we have to intervene And we have to implement an intervention, and everybody in the whole jurisdiction needs to get this intervention. And you as a researcher then become involved and you say, hey, but that would require you to do a before and after evaluation, which we know is not a robust design. We need to randomize. So let's randomize clusters and gradually roll out the intervention to all of the units in your jurisdiction. And then we have a more robust evaluation. So sometimes that can be a good reason because you then don't really have another choice. This thing has to be done in all of the clusters. A second reason that my collaborators often cite is that, well, you know, if you're going to tell me I have to do a parallel arm design, it means I have to recruit colleagues and other centers to participate in my trial. And half of them have to say, yes, I'll participate, when they know they can potentially get nothing. They just get the control. They're not going to get this new Cadillac intervention that everybody wants. So it's too difficult to recruit clusters to participate in this trial. A third reason is that people say, well, unfortunately, I have a limited budget, and I've got a limited number of clusters available for my trial. The stepped wedge gives me the sample size calculation that I want, so I'm going to choose a stepped wedge, because we know that a stepped wedge trial tends to be more powerful than a parallel arm design. It's very difficult for me to argue against that, because that's what they say. I only have this much in my budget, and I want to do this trial. Okay, well, the only choice then is a stepped wedge. So we have to think about that. Reason 4, people might say, well, I can't implement the intervention at the same time across half of my clusters if I were to do a parallel arm design. I like the stepped wedge because it simplifies the logistics. I can just gradually implement the intervention through time. Well, I have a big question mark there. Does it simplify the logistics? I will get back to that. Another reason, which is kind of towards the bottom of my list, is that people say, oh, I'm worried about bias. I think the stepped wedge allows each cluster to serve as their own control. So I want to do a stepped wedge trial because there's less risk of bias. The 6th reason, right at the bottom here, is that they say I have some sort of an ethical rationale. There's an ethical imperative. I've got to do a stepped wedge because it's unethical to withhold the intervention from some participants. My all-time favorite reasons, I've always wanted to try a stepped wedge. And it will make my grant more attractive to CIHR. I believe a few years ago there was actually a funding call that had examples of trial designs that would be attractive to them, and the stepped wedge was listed as one of the trials that was more pragmatic and that would potentially make the grant more attractive. So those are some of the reasons that I've come across. So let me go through them and then apply them to the example. So the first one, where somebody has made a decision already in the absence of the research that they're going to implement an intervention. And this is an opportunistic opportunity to do something that's more robust than a before and after design. So while I say it's a good reason, because the stepped wedge might be more robust than just a before and after, I find that it's seldom the case that governments are willing to randomize. They prefer a kind of a big bang implementation, or they prefer to intervene in the areas that need the intervention the most. So it's difficult to convince them that randomization is necessary. So you still have to convince them about the importance of the randomization, and you will have to explain to them that they can't, I've often received that request, can I make sure that hospital X, which is the worst performer in my health system, can we put them first, please? Well, no, so that's no longer a randomized design. So those are arguments that you'll have to make. So does it apply? Was that the reason they chose a stepped wedge in this point of care testing trial? I don't think that applies, because there was no indication in the manuscript that this algorithm was going to be implemented as a new Canadian treatment guideline. So I don't think that was the reason why they chose a stepped wedge trial. There was no indication that it was going to be done anyway. So the second reason, as I said, was it's easier to recruit clusters to the trial if they're all going to be offered something new. So it simplifies recruitment. On the other hand, why can't you, and this is reason that these might be conversations that I have with clinicians that I'm collaborating with. I say, well, could you consider a parallel arm design, perhaps of shorter duration, in which you give the control clusters the intervention at the end, maybe only if it's successful. So it could be that most of the clusters still get the intervention earlier than they would in a stepped wedge. So that's just an alternative. Think about, could you do something else? Like, could you give the control arm a minimal version of the intervention, maybe just some written guidelines rather than the full knowledge translation intervention? So there are options, there are counter arguments that you can make in this case. With a stepped wedge, like I mentioned, some clusters are going to have to wait really long before they get what they want. And they may lose interest and just give up. And I thought, well, if in fact the stepped wedge trial facilitates recruitment, surely we must see some empirical evidence of that. So I saw this systematic review that looked at 46 published stepped wedge trials. 31% could not recruit their target number of individuals, 20% could not recruit their target number of clusters, and 24% could not complete the trial within the planned duration. So certainly if we think that stepped wedge are going to make recruitment a lot easier, I'm not sure that we've got convincing evidence of that. Perhaps this is not a fair comparison because I needed a control arm of parallel arm designs to know how many parallel arm designs struggle with recruitment. And perhaps we need to do that systematic review. But I'm not convinced that that it's that easy to justify that it's going to facilitate recruitment. Does it apply to this example? I'm not sure. They don't really say if sites would have been reluctant to participate in the trial if it was just a parallel arm design. I don't know. That they don't say that they chose a stepped wedge to facilitate recruitment. The third reason is that my sample size calculation doesn't work out. So I've got a limited number of clusters available. So this one, I almost never manage to get anything out of the clinicians. Once they see that they need a smaller number of clusters, that's the design that they want. And I can appreciate that because trials are really expensive and often we just don't have that many clusters available. But on the other hand, we should always just check that the power calculations were correct and that we accounted for that correlation decay. And I think the comparator, if we are going to compare our sample size requirement under the stepped wedge, it should be a fair comparator. Perhaps we need to choose an efficient parallel arm design, just so that we have a realistic comparison. But on top of that, I think sample size for a stepped wedge trial with a limited number of clusters might not be a very good thing. Even though the power calculation works out, maybe we don't want to do cluster randomized trials with few clusters. They make sensitivity to the modeling assumptions just that much more. And so I feel good about stepped wedge trials with many, many clusters. I don't feel that good about stepped wedge trials with few clusters. Does it apply in this particular example? Let's just look at that quickly. So here's their stepped wedge design in which they needed 12 clusters over the 6 steps, 7,140 patients. Oh, sorry. If they had done a parallel arm design over 1 month, now I don't think it's probably not reasonable to expect a trial design just over a 1 month period, but if they were to do this trial in a very short amount of time, they would have needed way more hospitals than what is available. 172 hospitals, and I think there were probably only, what, 30 or something hospitals in Ontario. So they couldn't have done the trial as a parallel arm design. I can certainly see that. But if you look at a parallel arm before and after design, which is a lot more efficient, things are beginning to look better. So for this, they only needed 34 hospitals. So that looks a lot better. But what about a comparison like that? Could we have done a parallel arm design with a slightly shorter duration? So we have a parallel arm before and after design. Half of the clusters get the intervention and half just continue in the control. And then they can still get the intervention at the end. So for this, they actually needed the same number of hospitals if they had done that. And slightly fewer patients because it's 1 month shorter. So I don't know, maybe there were reasons why they didn't want to do that. But I'm just wondering if they perhaps considered this as an alternative design. So this is an illustration of the types of things that I might go through when I consult with a clinician wanting to do a stepped wedge trial. Well, here are the options. Now explain to me why this is not a reasonable option. So the parallel arm design would have given them a lot more possibilities for investigating the type of the effect of the intervention. Would have been at less risk of bias potentially. And so I think it's a reasonable alternative in this case. So I don't think the sample size consideration was the real reason they chose the stepped wedge, because they could have done a parallel arm design also with 12 clusters. So maybe that reason doesn't apply. So I still don't know exactly why they chose the stepped wedge. What about logistical feasibility? Well, like I said, the reasoning there is that, well, I don't want to, or I can't afford logistically to implement the intervention at the same time in half of my clusters. It's too much work. Well, that doesn't actually apply because we can do a parallel arm design with staggered implementation. I said earlier, we don't have to randomize once off. We can randomize in batches. And also, the logistical challenges with a stepped wedge, where everything has to be coordinated in calendar time, is a lot more than with a parallel arm design. You have to organize all of the ethics approvals right from the beginning because the sites have to be randomly allocated to a particular start time, and you don't know which site is going to be allocated to start first. So, and like I said, half of stepped wedge cluster randomized trials, if not more than half, are plagued by implementation challenges. So does it apply here? Well, I don't think so. Earlier on, we said that with a parallel arm stepped wedge trial over 3 pre and 3 post months, we would have needed also 12 clusters. So you could have done that parallel arm design in 3 waves, where in each wave you have 4 clusters, 2 allocated to the intervention and 2 allocated to the control. So it's exactly the same logistical burden as in the stepped wedge. Would have been a little bit longer to finish the trial, but perhaps that would have been a price that we are willing to pay. The 5th reason that people cite is because they think it's going to reduce bias, because each cluster serves as their own control. Well, that's only partially true. With a stepped wedge, the intervention effect consists of both within cluster comparisons, but also between cluster comparisons. There is a concurrent control, namely those clusters still waiting to cross. They have a concurrent control. And so if the randomization didn't work and they're not a comparable control, you know, that could be an additional source of bias. So on top of that, the intervention effect is confounded by time. I've already described all of these additional risks of bias that may not apply in a parallel arm design. So this is not a very good reason to adopt a stepped wedge design. And also, like I said, a stepped wedge trial, the analytical approach that we're going to use has specific assumptions about the type of intervention effect. And we don't have a lot of flexibility, or perhaps we just don't have the right methodology yet for looking at alternative types of intervention effects. So does it apply to this example? Well, I'm not 100% sure because they don't talk a lot about things that can help me understand the risks of bias here. They provide very sparse details about their analytical approach. So I don't know about all of these risks of bias, but what I thought to investigate is what is the type of intervention effect that we can expect in this trial? And so it happened to be the case that they published a single center interrupted time series study to examine exactly the same intervention. I hope you are familiar with interrupted time series studies. It can be a very robust design in which we look at repeated measures before, And after an intervention is introduced, then we look at intercept and slope changes in response to the introduction of the intervention. So they happened to do one of these designs at a single center, probably in preparation for this trial. And they published the type of, or the nature of the intervention and how the outcomes changed over time. And we can see that rather than a step change, there was a step change, but then there was a decay in most cases. So the transfusions tend to almost return back to baseline towards the end. So there was a definite decay over time when they looked at the outcomes over time. But this type of intervention effect, we will lose in our step wedge trial. We are going to get some sort of a time averaged difference. It's going to be a mixture of the decayed and the large effects. So we're not going to get a true unbiased effect of the intervention. We don't have the flexibility yet to examine that. So personally, I'm of the opinion that a merging of stepped wedge and interrupted time series methodology offers a lot of promise for more robust inference. If we can have more multiple or more repeated measures before and after in each center and combine that with the stepped wedge design, perhaps we can get stronger inferences and better understand what's happening to our outcomes over time. And then finally, the ethical requirement. So I don't think there is any, well, not myself, the ethicists, and there's a really nice paper at the bottom. They have debunked the idea that there is an ethical imperative for the stepped wedge. If there is an intervention that we believe is effective, we should just give it to everybody because we do need equipoise. We do need to justify randomization, and that's based on equipoise applying. And if it's unethical to withhold the intervention from some clusters, it should also be unethical to delay the implementation of the intervention at those clusters. And then also, besides that, in a cross-sectional design, not all of the individuals necessarily get the intervention. All of the clusters might get the intervention, but not necessarily all the individuals. So we could have completely different individuals in the control period than in the intervention period. So I don't think the ethical justification applies. And then the last two reasons, I've always wanted to try a stepped wedge, or it will make my grant more attractive for the funder. I don't know, perhaps we should look at funding rates for stepped wedge trials and parallel arm designs, but I don't think those are good reasons to choose this design. So, in conclusion, the stepped wedge design is a popular design. It has several advantages. Some of these might be theoretical advantages, but there are advantages, especially sample size requirements. It's really hard to argue with a statistically efficient design. So it does have some advantages, and I'm always very happy to learn about a stepped wedge trial that worked well. However, we should be conscious of the fact that this design is more complicated to analyze, it's more vulnerable to risks of bias, and we should think carefully, is a parallel arm design feasible? And perhaps that should be our preferred choice. So I have not been that successful in talking too many clinicians out of using this design. So I may have to stop worrying and learn to love the stepped wedge trial. So this could be my career going up in smoke because I've talked everybody out of doing stepped wedge trials. Or it could be investigators realizing that perhaps they should have listened to my advice and not done a stepped wedge trial. I don't know. That's all tongue in cheek. So.